So recording is started and I will continue from the slide where we were discussing some topics regarding introduction of reinforced concrete. Already the recording is uploaded and you can also uh, review the uploaded file. Now, in order to design reinforced concrete members, we need to first understand the design philosophies and the loads, load transfer paths, materials, their stress strain relationships, some equilibrium equations. So all the required information or the discussion we have inserted in the introduction lecture, and there are a few more slides which I will share with you along with the textbooks which you can read to make your understanding better regarding the design of reinforced concrete members. As I said in my previous lecture, we will start from beam elements. So and flexural design of beams will be our first topic, and Dr. Safir will also take up the flexural design of beams. The difference will be that I will talk about the ultimate strength design, and you people are also familiar with LRFD. So USD or LRFD design of reinforced concrete beam elements. I will discuss, and Dr. Safir will discuss using allowable stress design, the same flexural design of reinforced concrete beam elements. So before I discuss directly the design equations and section behavior, there are few slides which are important in introduction lecture which I want to discuss in online lecture, although the recording is already available. Design loads which we want to use to calculate the load on the structural members. Design loads include the self weight, which are termed as dead load, which do not change their magnitude and position with respect to time during service life of structure. And dead loads mainly consist of not only the self weight, but also the self weight of the reinforced concrete, but also the superimposed loads on such members. So the self weight can be easily calculated if you know the density of the material. Then density multiplied with the volume, you can calculate then the weight. So if you know the densities, you can easily calculate the self weight of the members. And in case of superimposed load, again, if you have the information about the densities of superimposed loads, as well as if you know the thickness of the floor finish, particularly in building structures, slabs, as I said in my previous lecture, are transferring the load to the beams and then beams to the column. So if slab load will be transferred to the beam, it means slab self weight, floor finish which is superimposed on the slab, its weight, and floor finish thickness type, density will be known to us, and based on that density and thickness, we can convert that superimposed load into pressure if I multiply the density with the thickness. If I will multiply the density with the volume, I will get weight. If I will multiply the density with the thickness, and if the thickness is uniform over the area, then thickness multiplied with the density will give me the units of pressure. So in this way, actually the density and the volume, or the density and the thickness of the floor finishes or superimposed loads, we will be using to convert them into the loads. Then comes the live load. Live loads consist mainly of occupancy load in buildings and traffic loads on bridges. They may be either fully or partially in place or not present at all. Like on Sunday, civil department, there is a holiday and there is no live load or students present in the department. So on all the floors, we have zero live load. And it may also change in location. It means that in one room, if students are present, it is possible in next room, there is no class, and then in very next lecture, the room which was vacant is now occupied by the students, by the live load, and the one which was preoccupied is empty. So it can change the location, and there may be 100% students, there may be 50% presence. So fully or partially presence on the slab is quite possible, and accordingly live load may be 100% or 50% or 30%. Their magnitude and distribution at any given time are uncertain, and even their maximum intensities throughout the life of the structure are not known with precision. So it means there is a probability attached, variability is there, but guidelines are present which can help us to decide the occupancy load with reference to type of the buildings. The minimum live loads for which the floor and roof of the building should be designed are usually specified in the building codes that governs at the site construction. So it is important that there are guidelines available in building codes. The specified loads are given, and on slide number 17, densities of the commonly used construction materials and the occupancy loads which are commonly encountered are summarized. So let me off the time and date. Now, densities, you need to keep them in mind. For plain cement concrete, 2300 kg per meter cube is the good value. For reinforced cement concrete, 2400. For brick masonry, 1900 to 1930. Earth sand, brick ballast 1600 to 1800 depending upon the degree of compaction. Quite safe is that you assume 1800 for the brick ballast or earth compacted sand, and these are densities, and once you multiply them with the thicknesses you can convert them into pressure, or in this way we can calculate the loads of such materials. Second important is the live load. In live loads we have residential, house and classroom loads. Like in civil department, I would say uh, if students are present on the first floor slab, the live load used will be 200 kg per meter square. So here the load is given in terms of pressure, load per unit area. So this m square is in superscript. So this is the pressure in kgs. You can convert it into Newton by multiplying it with 9.81, and further if you want to convert it into kilonewton you can divide the answer with 1000. So important occupancy loads: offices, library, reading rooms, stack rooms, warehouses. So you will find that increased the trend of live load is increasing downward, because in warehouses, godowns there is a heavy storage, so the proposed live load intensity is bigger as compared to ordinary residential apartments, houses. So once you know the building type, as a designer you will be informed regarding structural use, and accordingly you have to select the live load for your design calculations. And during the service life, that building should be then subjected to the type of load against which the building was actually designed. But if there is a change in the structural use, then one need to consult the designer again, that if the change in the structural use is decided, then what will be the new live load which will be superimposed, and then the designer will have to do the capacity analysis to determine that whether under the revised load the building can still survive, the slabs or beams and columns can still serve the intended function. If the answer comes out to be yes, then the permission can be granted. But if the change in the structural use will make the loads bigger and factor of safety is compromised, then obviously the permission will not be granted, or otherwise strengthening of the structure may be proposed. So at the stage of designing, designer is very well informed regarding the materials which are to be used, their corresponding loads and the structural use, and then based on them calculations are carried out, and the designing is done based on those anticipated design loads. Now once I have the information regarding loads, I know the structural use, and I have architectural working drawings where I can see how much are the sizes, column spacing, room dimensions, story heights. So I have all the information with me. Then the next step will be that knowing each and every geometric details along with the selected materials which will be used for the construction during the construction. For example, if we decided that reinforced concrete will be our uh, construction technique, and rather than the steel building we are going for a concrete building, and we decided that in this building masonry used will be clay masonry, over the rooms floor finish will be brick ballast, and then on brick ballast tile work will be done. We have decided the structural use that this building will be a residential apartment building. So in this way, after all this information, then comes what design philosophy will be selected, whether you will go for ultimate strength design or allowable stress design. For both of them, factor of safety is important. So in whether it is allowable stress design or it is ultimate strength design, in all the basic design equations, important thing is factor of safety. So the basic design equation will be that applied action into factor of safety should be equal to internal resistance. So action should be equal to reaction. And in terms of action, we want to exaggerate that action, amplify it, and that exaggeration is actually factor of safety. And then some, I may say, some load factor, some amplification of the action would be made equal to the reaction resistance. So in this way, this factor of safety which is appearing in the simple design equation means maximum failure load divided by maximum service load. It means there will be a reserve capacity. For example, during the service life, if the building is subjected to a service load, dead and live load, without exaggeration of dead and live, without any addition of the selected dead and live, that will be termed as service load. Like dead load, suppose 500 kg per meter square in terms of pressure I am talking about, and live load 200 kg per meter square. So in terms of unit area, 500 and 200 are the dead and live loads. So it means together they will become 700 kg per meter square. 500 kg per meter square dead, 200 kg per meter square live. So these are service loads. And if the failure load, it means the structure has the reserve capacity, and instead of designing it for 700 kg per meter square, if it can take on 1000 kg per meter square, so that will be termed as maximum resistance offered by the structure. It means 1000 divided by 700 will then be the factor of safety. it means 10 over 7. So that is the reserve capacity, that if the structure will be loaded further, so the additional load will be applied, and the design load of 500 kg per meter square dead is increased to 600 kg per meter square dead, which was used in the calculation, and rather than 200 kg per meter square of live, they increased it to 400 kg per meter square. So it means exaggeration occurred, and total load applied is now 1000 kg per meter square instead of the service load 700 kg per meter square. So it means if building can still take this additional pressure, or a structural element can still take that additional load, it means the structure has the factor of safety, and the margin from 700 to 1000 it can take, because during the design factor of safety was there and some additional load was considered while making the design. So in deciding the factor of safety, following are the relevant points. Factor of safety will cover following uncertainties. Uncertainties due to applied loads. Applied loads, as I have given you example, that rather than 500 they made it 600, or live load increase from 200 to 400. The other possibility is that once you will do the design, you will use some material strength, concrete strength, steel strength, you will use in your calculations. But if at site we discussed demerits of concrete, that concrete is a man-made material, and at site quality control is not as good as the other factory made materials enjoy. So in concrete casting, cast in situ, poor workmanship, lack of attention during mixing, curing, compaction can create drop in material strength. So that will then affect your design strength. And without factor of safety, it means you will be in danger, because if your desired strength was against a load of 700 kg per meter square, and using that 700 kg per meter square and material strengths, you calculated the cross sections and steel details, but sadly the used material strengths were unable to achieve at site. So it means you are now compromising on the structure capacity. So it means structure can't then sustain that 700 kg per meter square pressure. So as a result, there will be a drop in capacity. Unexpected behavior of structure, maybe sport settlements, some cracking in the concrete structures, diagonal cracking due to shear, poor bond between steel and concrete, thermal stresses, improper fabrication, some compromise on the cross section size, and some residual stresses which may be developed, and in your calculations those stresses were not considered. So these are the uncertainties, and to overcome them, always factor of safety is used to design the cross sections. Now this factor of safety, which is covering so many uncertainties, if it is provided at service loads, deflections and cracks are within limits. So this statement means that if you have incorporated a factor of safety and you have some reserve capacity, what benefit you will avail will be that at service loads, serviceability requirements, which are that the deflection should be minimum within limits and crack width is not more than permissible. Micro cracks, hairline cracks are permissible. So if there is a factor of safety, then you will get this benefit that neither the excessive deflections nor widened cracks will appear, and structure will pass the serviceability checks. And furthermore, since your structure will have some reserve capacity above your designed one, above your service required one, then it means some unexpected loads during natural disasters, earthquakes, cyclones. In such events, the reserve capacity will also help you to improve the ductility and also to give you life safety. And in this way, the structural performance can be improved during natural disasters. Now, ultimate stand design is based on the philosophy of dividing this factor of safety, which covers so many uncertainties, in such a way that bigger part of this factor of safety is applied on loads and a smaller part of it is applied on material strengths. So actually, in ultimate stand design, in your equilibrium equations, or I would say rather than equilibrium, you will say in your design equation, like on slide number 18, we have mentioned a simple design equation that applied action into factor of safety is equal to maximum internal resistance. So it means if on applied action I will put some factor of safety, and also on internal resistance I also put some factor of safety. So what I am doing, I am increasing the applied action by using a factor of safety more than 1, like 1.1 or 1.2. I am increasing 10 to 20% the applied action. And on the right hand side, I am decreasing the internal resistance by 10 to 20%. So it means I am multiplying internal resistance with 0.9 or 0.8. So on the left hand side, factor of safety is more than 1. And in resistance side, factor of safety is less than 1. So in this way, I am writing my equations under ultimate strength design as that I will have a material strength greater than or at least equal to applied load into factor of safety 1 into factor of safety 2. It means applied load will be multiplied with factor of safety 1, which will be greater than 1. And factor of safety 2 will go in denominator. And when I will take reciprocal of it, it will become less than 1. So this factor less than 1 will drop the resistance offered by the material. So in this way, my equation of action and resistance carries on both sides factor of safeties. So together then I can write it in equation as that the nominal strength, nominal resistance, which is without any factor of safety, which is the actual resistance, if I multiply it with a factor less than 1, we call it reduction factor, strength reduction factor. So the internal resistance multiplied by the reduction factor, which is less than 1, should be at least equal to the required strength, which will be calculated by multiplying the applied actions with some load with some factor of safety, which is above 1, and we call it load factors. So it means the equation is carrying on both sides factor of safeties. On the right hand side, it has factor of safety more than 1, and we call it load factors. And on the left hand side, it has value less than 1, and we call it capacity reduction or strength reduction factors. So in this way, whether it is movement or shear or load, we can write general equations as nominal into reduction factor should be at least equal to or greater than the applied action, which is exaggerated by some factor of safety. And we are using a subscript U, and this is used to state that it is ultimate movement, ultimate shear, ultimate load. So ultimate means that the service movement or service shear or service load multiplied with factor of safety, which are load factors. Now, if on this slide, very briefly, we want to compare allowable strength or allowable stress design with the ultimate strength design. Dr. Safir will talk in detail about the ASD, but very briefly on this slide, we can very easily judge that in ASD versus USD, where will be the difference? In ASD, in this stress strain curve of concrete, you will notice that in very initial range, when you apply stress on the concrete, the stress strain will be nearly straight. The curve, rather than curve, it will be nearly a straight line in the portion very close to origin. So in this portion it will be almost linear, and steel we already know that it is linear elastic up to yield limit. In allowable stress design, you will be working on service loads without any factor of safety on the loads, which I discussed in ultimate strength design, that factor of safety on both sides of the equation. On load side, we are having a factor of safety greater than 1, and on the resistance side, we have factor of safety less than 1. In ASD, what will happen? You will not put any factor of safety on the load side. Whatever service loads, you will calculate dead and live, and based on them the pressures, and then converting them into loads without any factor of safety or load factor, you will calculate the applied action. But in resistance offered, internal resistance, you will use the concrete stress only 45% of its peak. So what you will use, you will say concrete resistance offered is actually 0.45 FC prime, very close to 50%. 0.45 FC prime will be the stress which will be used. And in terms of steel, since reinforced concrete is a composite material, if I am working on a plain cement concrete cross section, then it's enough that only I will talk about concrete, and I will say that applied action I will equate with the internal resistance, and that resistance will be calculated using 45% of the peak strength of concrete. That's it. But since I'm using a composite material, composite of steel and concrete, so I have to decide both the materials, where will be the stress magnitude in that material. So in allowable stress design, for a composite material concrete, reinforced concrete, you will stress your concrete against applied action to maximum 45% of FC prime, and your steel to 40 to 50% of yield strength, 0.4 to 0.5. 0.5 for steel of grade 280 or 300, 280 or 300 yield strengths are lower grade steels, and 0.4 when you are having a steel of grade 420, 413 or 420. So hardly, I will say that 40 to 50% of the yield strength, half of yield strength, I may say, and half of FC prime, peak strength. So both the materials are stressed to almost half of their limit. So it means factor of safety, total factor of safety is on the material side, that you are not putting any factor of safety on the service loads, but all factor of safety is on the material strength, and you are using the material strength hardly 50%, almost 50% of their maximum or peak. In both allowable strength and ultimate strength design, important thing is analysis, whether it is ASD or USD, analysis will be carried out in elastic range. Analysis is not plastic. Analysis is elastic. However, in allowable stress design, analysis is elastic, and almost materials you are using are also in the elastic range. Concrete will be nearly non-linear when you will approach 45% FC prime, but still non-linearity will not be too obvious, and it will almost be on the linear branch in the stress strain relationship, although the curvature will begin right in beginning, but not that big as it will be beyond 50% of FC prime. But whether it is the allowable stress design or ultimate strength design, our analysis carried out will be elastic analysis. However, in ultimate strength design, we will stress the materials to their non-linear limit. We will not be using the elastic range only. So in USD, there is a nice combination of analysis is elastic, but design or sectional behavior is inelastic. So it is a nice mixture of elastic and inelastic. Analysis elastic, design inelastic. However, in ASD, analysis and design both are in the elastic range. In plastic design, plastic analysis is carried out in order to find the behavior of a structure near collapse load. So non-linear state, non-linear analysis, and non-linear design. In this type of design, material strength is taken from inelastic range. So not only the analysis is inelastic, design is also in the inelastic range. So that is the reason it is more economical. But for design office practice, it is quite tedious. It is observed that whether the failure is sudden or ductile. So based on the plastic analysis, failure load can be estimated, and failure mechanism can also be explored. Ductile failure is most favorable because it gives warning before failure of structures. So in reinforced concrete, members, we can carry out plastic design, we can determine the collapse load, but it will be for review purpose, to review the capacity of structures, to determine the failure mechanism. This analysis can be carried out. However, in new construction, in new design, we normally perform ultimate strength design, in which analysis will be elastic and design of the cross section will be based on the inelastic range of the material strength. So full material capacity will be utilized while making the design based on elastic analysis. And forces based on elastic analysis will be exaggerated by using load factors. And the material capacity used will be in the inelastic range, but that capacity will be dropped by using a factor of safety. And as I said, we call it capacity reduction factors or strength reduction factors. So this is a brief introduction about allowable strength, allowable stress and ultimate strength design and plastic design. Now in PRC1 and PRC2, we will get opportunity not only to analyze a structure, but also to design it. So when we are doing analysis, we are actually trying to find out what is the load carrying capacity of a reinforced concrete structure. So if you are given with all the design details, you are given with the structural drawings in which steel details, section details, material strengths are provided to you. So you know each and every detail of the structural members, starting from geometry to their material strength. The only thing asked is that give us what load this structure can take. So rather than providing you load and asking you that against this load, what would be the size and detailing of structural members, against this load, tell us what should be the cross section depth, cross section width, steel reinforcement area, concrete strength, steel strength. All make all these decisions and tell us that against this load, what are the structural details which are required. If this kind of question is asked, that I can give you one simple example, that you are asked that there is a load of 100 kilonewton per meter, a uniformly distributed load of 100 kilonewton per meter, and against this load tell me what should be the beam cross section if this load is to be present on a span of 3 meters? So this is a direct question, that there is a 100 kilonewton per meter uniformly distributed load on a span of 3 meter. It is a line load, and I want to place a beam under that line load, which is having a span of 3 meter, and the load is 100 kilonewton per meter. So question is that, can I put this load safely on a line element, and that element I select is a beam on which I can put this uniformly distributed load, and beam span I'm proposing is 3 meter. So you will be asked that, please tell how much cross section of the beam is suitable on a span of 3 meter, which can take this 100 kilonewton per meter. So it means you will be asked that to provide that, for example, to take this 100 kilonewton per meter load, they are expecting that you will give an answer like this, that a beam of size 228 millimeter 9 inch by 1 feet 300 millimeter with 2 bars of grade 420, and each bar has the dia 19 mm, and concrete in beam is of 20 megapascal FC prime, and steel which you selected 2 bars are of grade 420. So they are expecting that you will finally will reply with this answer, that a beam with this cross section 228 by 300 with 2 bars of 19 mm 420 grade concrete of grade 20 can take on this 100 kilonewton per meter on a span of 3 meter. So when you will reply like this, you are actually then responding with a design of a beam cross section. So against action, you are designing the cross section, and you are giving each and every detail, cross section details, material strengths, sketch. So that is called design of a structure. But if the question is reversed, you are given with a beam of 228 by 300, and you are given with 20 megapascal and 420 grade steel. जी अस्सलाम वालेकुम, जी अस्सलाम वालेकुम, जी आ रहा हूँ. So you are given with this cross section and steel and material details, and you are questioned that tell what load this beam can take if the beam span is 3 meter. Now the question is reverse. You are given with the drawing, each and every detail, span, and you are asked that, can you tell us what is the capacity of this beam? Now they are expecting that your response should be that this beam can take 100 kilonewton per meter. So this is called capacity analysis. That against a given design, what load can be safely applied on that member. It is called capacity analysis. And design means a load is given and you need to decide what are the section details and what strengths should be used to take on that load. So in this way, we will be able, at the end of this subject, we will be able to carry out not only the capacity analysis but also the design. So I think at this stage I may stop the recording and let's have 10 to 15 minutes break.